Hello guys, in this video we are going to see how to write Lewis structures. But before that, I would like to remind you that I am also on Patreon, where you can find the PDF of this lesson, and also you can find additional material, and also I am building my course about organic chemistry lab techniques. So first of all, what is Lewis structure? Lewis structure is a way to write the structure of a molecule, or also ions, or even simply elements, using the octet rule and the valence electrons. These Lewis representations consist of dots or dashes. In these representations, dots are used to indicate the valence electrons. One electron above one atom indicates an unpaired electron. Two dots above one atom indicates a lone pair. You can also use dash instead of two dots if you prefer. On the other hand, two dots, or again a dash between two atoms, indicates a bond. Let's start to see the Lewis symbol for elements. Elements are indicated with the symbol, which is a letter. You can find in the periodic table, for example, hydrogen is H, carbon is C, and so on. But with Lewis representation, we have also to indicate the valence electrons of that element. The valence electrons are easily obtainable from the periodic table by checking the membership group of that element. In more detail, the valence electrons correspond to the group number for the first two groups of periodic table. For example, let's take group 1. The number of valence electrons for group 1 is simply equal to the number of groups, so is 1. So hydrogen, for example, will have only one valence electron. And so for lithium and all of the other elements in the same group. Group 2 will have 2 valence electrons. Now, if we move on group 13, since between group 2 and group 13 there are the transition metals in between, we have that the number is now 13 and not 3. So how to calculate the number of electrons from the group 13 till the group 18? It's simple. You have to take the number of the group and then subtract the number 10. For example, the valence electron for group 13 will be given by 13 minus 10, which is equals to 3. For group 14, the number of valence electrons will be given by 14 minus 10 equals 4, and so on, till the last group, which is the group of noble gases. In this case, the valence electrons will be given by 18 minus 10 equals 8. These valence electrons represents the number of electrons that each element has in their outer shell of their atom. We take the valence electrons because the valence electrons, since they are the outest part of the atom, these electrons will be involved in reaction. And so these electrons will explain the reactivity of all the main group elements. For example, hydrogen, as we have already seen, is represented by one unpaired electron, because hydrogen has only one electron in its 1s orbital. If we take lithium, lithium has the exact same valence electrons representation than hydrogen, because lithium has one electron in its outer shell, even if it has also 2 electrons in the inner shell. But these 2 electrons are not considered in the Lewis representation. So now it's very simple to write the Lewis symbols for all the main group elements just by using this table I have prepared for you. As you can see, for each element of the same group, you will have the same number of valence electrons. For example, let's say that I have oxygen. Oxygen belongs to the group 16 in the periodic table. So you have to look at the column in this table regarding the group 16. You have just to exchange the X letter with the O letter and you will have already the Lewis symbol for oxygen. And what about sulfur? Sulfur is in the same group of oxygen. So the representation for sulfur will be pretty the same, only you have to change the letter. So with this simple table, you can write now the Lewis symbol for all the main group elements. Why the electrons sometimes are unpaired electron and sometimes are like paired electron? This is because the electrons are reflecting the electronic configuration of the element. Let's take again oxygen. In the representation with the Lewis symbol of oxygen, we have 2 paired electrons and 2 unpaired electrons. Why is like that? Because the electronic configuration of oxygen, but also the electronic configuration of all the elements in that group, consists of 2 electrons in s orbital, which are paired electron. Then you will have 2 paired electrons in one p orbital, and the last 2 electrons will be unpaired electrons. There is a reason why they're written like that. It's not by chance, okay? So, now you are able to write the Lewis symbols for all the elements. Let's move to the second part of this video. How to write the Lewis structures for molecules and for ions. The Lewis structures for molecules and for ions are based on the Octet rule. What is this rule? Octet rules says that one element combines with another element in order to reach the stability. And this stability is given by 8 number of electrons around the element. Why there is the rules of 8? Because if you take into account the noble gases, they are elements which do not react so easily with other elements. So they are pretty unreactive because they have 8 electrons in their outer shell, which confer them stability. So if your professor is asking you, write me the molecule of neon, don't fall into deception. The molecule of neon is simply one atom of neon, because neon will not easily combine with other elements. If we see how neon is made by 2 inner shell electrons in its N1 energetic level, and also has these 8 outer electrons, the valence electrons, in N2 energetic level. So are these 8 electrons outside the neon which are giving to it the stability. So the octet rules says that each element will try to reach these 8 electrons around them, and they will do that by combining with other elements. For example, oxygen has 6 electrons in its outer shell, so 6 valence electrons. So this means oxygen needs 2 more electrons to reach the octet rule, so to reach stability. And this means that oxygen will try to do 2 more bonds. And this is actually what happens in water when oxygen binds to hydrogen. However, there are some exceptions to these octet rules. Let's see them. This exception is called the duet rule, and it's valid for hydrogen and helium. Hydrogen and helium, they need only 2 electrons to reach stability. This is due to the fact that they have only one s orbital, and one s orbital can be filled only with 2 electrons. Second exception is the so-called expanded octet. What does it mean? It means that there are some elements, such as the elements from the third period and beyond, such as sulfur, silicon, but also chlorine, bromine, or even phosphorus, which can react and have around them not just 8 electrons, but 10 electrons, or even 12 electrons. That's the reason why it's called expanded octet. This happens because these elements have also the electrons they can use for making more bonds. On the other hand, there are also elements which will have the so-called incomplete octet. For example, elements like boron and aluminium, they need only 6 electrons to reach stability. The same is true for beryllium, which needs only 4 electrons to reach stability. The octet rules is also not valid for transition metals elements, because these elements are not even considered for the Lewis model. We need more advanced method. Now let's see how to write these structures. I will show you the 4+2 rules, which can help you to do your exercise in a brief and straight to the point way. Why I call that 4+2? Because the first 4 rules you have to use it all the time, and the last 2 you have to use only in some cases. Let's start. First rule: count the valence electrons which are around all the atoms, sum them up, and then divide everything by 2. Let's do an example. Let's take the ion NO3-. So if we have to write the Lewis structure for this ion, we have to follow this first rule. So let's see the valence electrons for each atom. Let's start from nitrogen. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, but we have 3 oxygen in the molecule, so we have to take this into account and consider 3 times 6, which equals 18. But also, we have to add the electrons, which is present in the sign minus. Be careful about that. So, all the valence electrons of elements, but also eventually electrons which are part of the minus sign. So, let's add also this minus sign, which corresponds to 1 electron, and then let's sum everything, and we will gain 24 valence electrons. Let's now divide this 24 by 2 in order to have the pair of valence electrons, which is 12. Before going to the second rule, I would like to underline that the valence electrons are the electrons we have to use in order to build our structure. So keep these electrons on one side, because we will have to use it for building our molecule. Second rule: place the least electronegative elements in the center of your molecule. Why? Because the least electronegative elements will be also the elements which will share more its own electrons with other elements. So it's more likely that this kind of elements will be in the center of molecule in order to do as much bond as possible. Let's be back to our example, the nitrate anion. For this anion, the least electronegative element is nitrogen. You can check it in the periodic table. If you have a good periodic table, you will see there the Pauling electronegative numbers, which is a measure of electronegativity. And you can see which atoms is more electronegative or less electronegative than another. And you can see that nitrogen is less electronegative than oxygen. So we have to put nitrogen in the center of our molecule, and you can also already start with the first single bond between nitrogen and these 3 oxygen, just to start. Be careful because sometimes this rule has some exception. Let's take for example CH4. In the case of CH4, hydrogen is slightly more electronegative than carbon. However, carbon will be in the center of molecule. Why? Because hydrogen, as we have seen, can do only one bond. So you cannot put an hydrogen in the center of molecule and forming 4 bonds. Is simply not possible. So this is a general rule, but it's valid most of the time. Let's go now to the third rule. So calculate the pairs of electrons which are involved in the formation of bonds. How to do that? We have to calculate, first of all, the total octet electrons. What does it mean? We have to see which elements are following the octet rules, which elements are following the duet rules, which are forming the expanded octet or the incomplete octet, and sum all the electrons each element needs around itself in order to be stable. Sum all of these electrons together and then divide by 2 in order to gain the total octet pairs of electrons. So the sum of octet, incomplete octets, extended octet duets must be subtracted to the pair of valence electrons we have calculated before. In this way, you will gain the bonding pairs, which is highly important to understand how many bonds we have there. Let's do an example. Let's be back to our molecule. Nitrogen and oxygen both follow the octet rules. What does it mean? That we have to count 8 electrons for each element. So 8 electrons for nitrogen, 8 electrons for oxygen, but since we have 3 oxygen, it will be 8 times 3, which equals to 24, and then sum 24 plus 8 electrons of nitrogen, and you will gain 32 electrons. Divide these electrons by 2 in order to obtain the pair of electrons, and the result is 16 pairs of electrons. So these are the total octet pairs of electrons. Now you take this number and you have to make the difference between these pairs of electrons with the valence pairs of electrons, which we have calculated before, and it was 12. So 16 minus 12 is 4. This means that we have 4 bonds in the NO3 molecules. 3 bonds we have already placed, so we need to place the last one. This means that NO3 has a double bond in the molecule. Now we have 4 pairs of bonding electrons which have been settled. 4 rules. Place the remaining electrons as lone pairs, in order that each atoms will follow the octet rules. If we are back to our example, we have already settled 4 bonds, so 4 pairs of electrons. But we had calculated before 12 valence electrons to be used. So this means that we have still 8 pairs of electrons to place in our structure. These 8 pairs of electrons will be placed in a way that each element will reach the octet. So let's start from nitrogen. Nitrogen, as you can see, is forming 4 bonds. This means that since each bond gives 2 electrons contribution, this means that our nitrogen has already complied with the octet rule. So there are already 8 electrons around nitrogen. We cannot put any more electrons on nitrogen because it's already stable. So let's see oxygen. We have 2 kinds of oxygens there. One kind of oxygen is the oxygen with 1 single bond. As you can see, this oxygen has only 1 bond. This means that they have only 2 electrons around them. So we need to put 6 electrons in order to have 8 electrons around oxygen. This means 3 pairs of electrons. Let's put these 3 pairs of electrons as a lone pair on these 2 oxygen. The last oxygen has 2 bonds with the nitrogen. This means that around this oxygen there are 4 electrons. So, if we put our last 2 pairs of electrons as lone pair on this oxygen, we have also reached 8 electrons also for this oxygen. So, all of our 12 valence electrons are now placed, and all of our elements have now followed the octet rule. We need only to write the minus charge, and we can do that just putting brackets and the minus sign outside. Is it hand? Let's see. The 5th rule is about topic of resonance. 5th rule. See if there are some resonance structure for your Lewis structure. What does it mean? Resonance is a concept in which you will have the same placement of atoms but different placement of electrons. And all the resonance structure are equivalent in terms of energy and all valid. Let's do an example again with our anion. For the nitrate anion, the structure we have written is the right one. However, as you can see, the double bond can be equally placed in another position involving another oxygen. In this way, we can write in total 3 resonance structures for nitrate anion. In this case, arrow with double tips will be used to indicate that these resonance structures are all valid and they are interchangeable, because the electrons actually which are involved in this double bond, they are delocalized on all the molecule, because they are actually involving all of these 3 oxygen. Why these electrons are considered delocalized? Because by experimental findings, it was demonstrated that the length, in this case, of this kind of bond is an intermediate length between the single bond and the double bond. So it's like intermediate, it's in the middle. This means that this kind of molecule, like our nitrate anion, is forming bonds which are between the single bond and the double bond, because this double bond actually is shared with 3 atoms. That's the concept and the topic of resonance. So, 5th rule, see if there are possible resonance structure in your molecule and write them, just by watching if there are double bonds which can be placed in an equivalent position in the same structure, without changing, of course, the position of atoms. Now, let's see the last rules. Sometimes, when you are writing or doing exercise with Lewis structures, you will find that there are different kinds of possible Lewis structure, which anyway, they looks like right. So you need in this case to use this 6th rule, which states, calculate the formal charges for each atom in each structure and see which structure has the lowest formal charges on non-metals element, because this structure will be most stable. But what are these formal charges? Is actually the charge which is describing the behavior of that atom inside the structure, because in that structure the elements could have acquired or given away electrons. In this case, the charge is telling us if that element has more electrons than its valence electrons or has lost electrons during the formation of the structure. How to calculate the formal charges? There is a formula for that, which is this one. Formal charges equals the valence electrons minus parentheses lone pair electrons plus half of the bond electrons. Let's apply this to our nitrate ion. How we can calculate formal charges for our ion? Let's start from nitrogen. Nitrogen has 5 electrons in its valence shell. So it's 5 minus In the structure, it has 0 lone pair electrons, so we can write 0, plus half of bonding electrons, which are 8. So we will have 5 minus 4, which is plus 1. So plus 1 is the formal charge for nitrogen. So as we can see, nitrogen in this structure has lost 1 electrons. Let's see the oxygen which are forming one bond with the nitrogen. In this case, oxygen has 6 electrons in its valence shell. So we have to write 6 minus parentheses 6 electrons as a lone pair minus half of 2, because there is only one bond. So we'll have 6 minus 7, which is minus 1. So we can write minus 1 or even only the minus sign on these 2 oxygen. Let's see the last oxygen. The last oxygen is the oxygen involved in the double bond. We will have again 6 valence electrons minus this time 4 lone pair electrons minus half of 4. So it will be 6 minus 6, which is 0. So we can write 0 as formal charge for this other oxygen. So those are the formal charges we can write in our nitrate ion. There is also another way, which I'm using, to calculate formal charges even if you don't remember the formula. Let's see this, because it can help you if you have a, blackout of your mind during the examination and you don't remind the formula we have seen. Let's see this more visual method. For this visual method, you have to divide or imagine to divide your bonds by 2. And then count the electrons you have around all the atoms, considering that now the bond is divided by 2, so the contribution of that bond is not 2 electrons, but now is only 1 electrons, because we are divided in 2 pieces. Simple. So let's count how many electrons has now nitrogen after this division. Nitrogen will have now 4 electrons. Simple. Which is the valence of nitrogen? The valence of nitrogen is 5. So just do 5 minus 4 is plus 1 as before. Let's repeat this with oxygen. Oxygen with one single bond. It will have around it, as you can see, 6 electrons from the lone pair plus 1 electrons from the divided bond. So this oxygen has 7 electrons around it. But the valence of oxygen is 6. So just do 6 minus 7, it's minus 1, as before. Last oxygen. The last oxygen has 4 electrons from the lone pair and 2 electrons from the double bond divided by 2. So it's in total 6 electrons. The valence of oxygen is 6, so 6 minus 6 is 0. So this is another method you can apply for the calculation of formal charge. But let's see now when we have to use and why we have to use the calculation of formal charges. In the case of nitrate ion, it was pretty useless, because this is already the right structure. We do not have other structure, so we are pretty sure this is the final structure. But there are some cases in which, as I've already said, we will have more than one, or we can be unsure about some structure they are well written or not. So in this case, you have to use formal charges calculation. Let's do an example. Let's say that during your examination, your professor is giving to you sulphate anion. Sulphate anion, there is sulfur there. Sulfur is an element we have already said, which can have expanded octet. This means that you don't know if in this molecule sulfur will follow the octet rule, and so we'll have around it 8 electrons, 10 electrons, or even 12 electrons. How can you know? So most likely you will write 3 structures. One considering the sulfur following the octet, one considering the sulfur following the expanded octet with 10 electrons, and another one considering sulfur with 12 electrons around itself. So you will have this tree structure. Which is true, which is fake? Apply these last rules. So write the formal charges. Let's write the formal charges for all of these three structures as I have taught you before. You will have this result. As you can see, if we take the structure in which sulfur is following the octet rule, you can see that the formal charge for sulfur is +2. +2 is too high for a non-metals element because it's not the behavior of non-metals element to have positive charge on themselves. It's more the behavior of metals. So this is not stable. Let's go to see the second one following the 10 electrons rule around it. In this case, the charge for sulfur is +1. It's better than the previous one, so structure is for sure more stable than the previous one, but it's still a +1 charge on non-metals element. Let's see then the last one. The last one has 0 on sulfur. That's a lucky combination. This means that this is highly more stable than all of these two structures. So this is the most stable we have, and so this is the right structure we have to write during our examination. So this was the last rule. Following these rules, they can help you during your examination. They are not so well written in books, so I hope this video can help you to do your exercise without doubts. Please write me in the comment if this video was useful, and in the next video we will do some exercise on these Lewis structures, and bye.